only a couple segments left. We've assumed a couple times now that the direction of gravity for objects on the Earth is towards the center of mass of the Earth. How do we know for sure? To really answer that question, we have to delay a little bit of groundwork first. And the way we're going to do that is by asking, what is the work done by gravity? We know what it used to be. It's the force of gravity dot the displacement integrated from, position 1 to position 2. And in our old sort of pre-Newton's law of gravitation scenario, mg was the force of gravity, and we were just dotting that with the integral of dr, or in other words, mg in the negative, I guess the negative z direction, the like elevation direction, dot with delta r, the displacement. But now that we have Newton's law of gravitation, we know that the gravitational force might not be constant. If we're starting at the surface of the Earth going up, like towards space, the strength of gravity changes the farther away we get from the Earth. So we can't factor it out from the integral. It's not constant anymore. All right. So let's figure that out. The force of gravity. Well, we know what it is. It's capital G, mass 1, mass 2, over r squared. And that's in the r direction, the radius direction, the altitude direction. Negative r hat, right? R1 to R2 dot dr. Now, we're talking about radially outward from the center of the Earth. That's what this is showing us. And again, still we're making this sort of we're representing it like the gravity points towards the center of the Earth. The dr, the only displacement we care about is the displacement in that radial direction away from the Earth. And that's this r. That's the separation. So the minus sign, this r direction and this r direction. In other words, there's some magnitude displacement in the r direction again, because we're going to take the dot product. We only care about the pieces that are parallel. So we're talking about the integral now, g m1, m2. Those are constants, and we can pull them outside. What we're integrating is 1 over r squared dr from r1 to r2. G m1, m2. Now, this is r to the negative 2. So when we integrate, it's r to the negative 1. Wait, this minus sign comes out front. This minus sign from the antiderivative, evaluated from r1 to r2. That minus sign's still there. So, all right, wait a minute. We've got negative g m1 m2 times negative r2 to the negative 1 minus negative R1 to the negative 1. Okay. Give that a second to sit there, and then let me steal that and put it up here so I can work with it a little bit. We're saying that the work done by gravity is negative G M1 M2 negative 1 over R2 minus the minus gets us a plus 1 over R1. Now, gravity is a conservative force, which means that we can define, like we did before, a potential energy associated with gravity. The delta is always final minus initial. So, that means that the U1, U2 minus U1 is the negative of the work done by gravity. If we're going away from the Earth, gravity's doing negative work, negate that so it's a positive left-hand side, the final potential energy should be greater than the initial because we're farther above. We can fall more. Okay, this works. All right, but the negative of the work done by gravity, that's the negative of that integral we just took. So that's the negative of the negative G M1 M2 negative 1 over R2 plus 1 over R1. Minus R2 plus R1, it's backwards. This is U2 positive minus U1. So we got a minus sign in here someplace. Let's pull out a minus sign. And then we have G M1 M2 1 over R2 minus 1 over R1. So this looks like negative G, let's distribute, negative G M1 M2 over R2. I'm going to keep the minus sign and then rewrite the numerator with so here's the thing for R2, which is U2. Here's the thing for U1. So what we're forced to conclude is that this expression, this thing in a box, is what we're evaluating at point 2. And we evaluate the same expression at point 1. So generally speaking, the potential energy associated with gravity is negative G M1 M2 over R. Now, capital G is a constant, M1 and M2 are positive. That means the numerator is always positive, but there's a minus sign. So this is always negative. R, the smallest it can be is 0, right? If the two objects are right on top of each other and there is no separation between them, if they're any farther apart than that, R is also positive. This will always be negative, which is strange. It's kind of an odd thing where we always have negative gravitational potential energy. Okay, because it's only deltas that we care about. It's only the subtraction. As long as U2 is greater than U1, the delta is positive. Okay, so let's talk about lifting an object. From a height of 1 meter above the surface to 2 meters. Or, you know what, from the surface 1 meter up. Let's do it that way. Delta U, U2 minus U1. So U2, using this expression, would be minus G M1 M2 over the radius of the Earth plus 1 minus U1, which was the energy that we had on the surface. Negative G M1 M2 over RE. Okay. Which term has a greater magnitude? This one. Because this denominator is bigger. We're dividing by a larger number, that's going to give us a smaller quotient. So this term, which is negative, is going to be smaller than this term, minus the minus, which is positive. So the delta U is still going to be greater than 0, which is great, even though both individual potential energies are still negative. The delta is positive, like we need. It's because we're defining potential energy in terms of an integral. All we care about is the net change overall, not what the actual value is. So we end up saying this, and that's fine. The way we can get potential energy to be non-negative is by making R infinitely large, right? No matter, imagine that the Earth is the only thing in the universe, or that the sun is the only thing in the universe. No matter where you put the Earth relative to the sun in the universe, you could put them as far apart as you want. R is still going to be finite. It's stupid large, but it's a number. It's a real number that exists. So this isn't 0. Earth will always be attracted to the sun in that scenario. That if there's no other masses around to attract it, eventually the Earth will be attracted to the sun, according to gravitation. There's no way around that. The 0, the floor for potential energy, and when we were talking about NGH, we used to talk about where is the floor, right? Where is it that we have 0? The floor here is when we are infinitely far away, so that finite over infinite goes to 0. We are so far away that we have completely escaped the gravitation of whatever object it is we're talking about, whatever planet or star or whatever that we're talking about. Next segment.